Hey everyone, my name's Eve. I'm a software engineer on the Google open source security team. And today I'm here to present about proactive security in open source. Putting together this presentation, as you can see, was very much a team effort. So I want to start by thanking three of my colleagues who weren't able to be here today, but who all contributed a bunch to this presentation. So thank you, Chloe Chen, Jess McClintock, and Kelly Stewart for all your hard work. And I'm really excited to share this presentation with everyone here today. Today we're going to be talking about trust in open source software and how that feeds into proactive open source security. This is a quote from Ken Thompson's 1984 Reflections on Trusting Trust, where he emphasizes the gap between the source code you review and trust and the build artifacts that you actually use or deploy. In the time since this paper was published, the trust model for developers, particularly those of us who rely on open source, has only become more complicated, with the distance between the source code and the build artifacts growing ever larger. To illustrate the real-world implications of this gap, I'm going to go through 4 case studies of some recent supply chain attacks on open source packages like boltdb and XZ, which expose the way that malicious actors can deceive traditional source-level verification to insert malicious payloads into your software. Then we'll discuss a model for analyzing build artifacts in terms of the capabilities that they can access. And finally, we'll show how Capslock, a capability analysis tool, can be used to support source-level verification to bridge the gap between source code and build artifacts. Let's dive into some case studies. Firstly, an attack that happened in the Go ecosystem, which involved a malicious fork of the popular boltdb-go library. To understand how this attack works, we need to know a little bit more about the Go module proxy. For any die-hard Go fans, in the interest of time and simplicity, I am going to be hand-waving over a few of the details here, so please bear with me. When the Go programming language was first created, it differed from other package management ecosystems that you might be familiar with, like NPM or Cargo, by having the source code be the distribution format. Rather than having a centralized package manager, historically when you installed a Go package, the Go tool actually downloaded the package's source code directly from a host like GitHub. Then in around 2019, the Go team launched the Go module mirror. Now, instead of going directly to the source code, the Go tool will by default query this module mirror, which will fetch the relevant source code, store an immutable copy of it, and then serve it to you and any other Go users. This model comes with a ton of benefits, including improving the performance and reliability of using open source Go code. But it can also be taken advantage of, which was precisely what happened in the case of boltdb. boltdb was a legitimate library which implemented a simple key value store and had over 14,000 GitHub stars. In November 2021, someone made a fork of this library, and the fork was called boltdb-go/bolt, which is obviously and intentionally very similar to the original name, with just the -go suffix added. Soon after the fork was created, the owner of the fork published some malicious code to GitHub, tagged as version 131. This code contained a backdoor that established a connection to a remote server, allowing attackers to send and execute commands on the infected system. That version then got pulled into the Go module mirror, which would have left the mirror in a state like this. So had any Go developer tried to use boltdb-go/bolt at version 131, they would end up downloading this malicious backdoored code from the Go module mirror. Now, this is a pretty suspicious state. Any developer who had gone to the trouble to look at the source code repository at version 131 would have pretty easily been able to see that something weird was going on. So what the attacker did next was to create a clean commit and then point tag 131 to the clean commit. Now, if any Go developer tried to inspect the source code for 131, they'd see a perfectly clean repository with no malicious code. What's interesting about this attack is that there was only one other package, which was a cryptocurrency library, that ever depended on this malicious fork. So this was clearly a very directed attack, and we can be almost certain that the cryptocurrency library was its target. The PR to start using the fork was likely made by the attacker, who'd been contributing small changes to that cryptocurrency library for about a month. The PR that added the dependency on the fork was big, hiding the change dependency amongst a large number of spurious formatting changes, which were probably intended to overwhelm the reviewers and to decrease the chances of detection. And those tactics were successful. The PR got merged on the 3rd of November. Some time passed, and in August 2022, the cryptocurrency package that was using the malicious fork actually ended up getting archived. Despite this, due to the way that the Go module mirror caches the version, that malicious version continued to be available for over 3 years. It wasn't until February of 2025 that Socket's AI scanner flagged the boltdb-go/bolt package as malicious, and Socket researchers published their findings disclosing the attack. This led to both the package being removed from the Go module mirror and the threat actor's repository and account being removed from GitHub. So what can we take away from this incident? One big thing to note here is that the strategies used by attackers to bypass detection almost all focused on tricking human source code reviewers. The most obvious is in that initial typo squat in the name of the fork. Here the attacker chose a name that was really similar to the name of a popular and a legitimate library. It's a name that plausibly sounds like something that a reviewer would expect to see. This helped to ensure that when they added the dependency on the malicious package to the target library, it didn't stick out as something obviously suspicious, like if the package was called evil backdoor package or something. Secondly, the commit that added the bad dependency to the cryptocurrency package also included thousands of lines of formatting changes and other irrelevant details, spread over multiple files, to intentionally increase the difficulty of manual code review. I'm sure anyone here who does code reviews knows how challenging a PR with thousands of lines of code would be to review, and it's all too easy to see how something like this could slip through. Finally, the attackers used Git tag mutability and exploited the caching of the Go module mirror. After initially publishing that malicious version, we saw how the threat actor ensured that it was cached indefinitely and then rewrote the GitHub tag to point to a clean, legitimate version of the package. This was a deliberate deceptive technique to hide traces of the malware from any manual code review on GitHub. So even if a developer was being really diligent and checking the source code of their dependency, they wouldn't have found anything suspicious. While the boltdb incident relied on a lot of things that are specific to the Go ecosystem, it's not just the Go ecosystem where attacks like this happen. Let's look at another case study, this time taken from NPM, where the author used package versioning to hide their malicious changes in plain sight. EventStream is a helper package for working with streaming data, but it hadn't been in active development for a couple of years. Its author had a lot of other things going on, so they let maintenance of the package fall by the wayside. So when a user contacted the author and offered to take over the project, the author understandably saw it as an opportunity to shed some responsibility and handed ownership over to this person. The problem was, as you may have guessed, that this person was a hacker. The latest legitimate version of the package had been published about 2 years ago and was version 3.3.5. The malicious actor published the new vulnerable version as version 3.3.6. But that's not all. After releasing that infected version, the attacker also published another clean version, version 4. Why? Well, this was part of the genius of the deception. Because of how versioning works in NPM, most projects that depended on EventStream would have used a requirement like _3, which would automatically update to the latest minor version. But that type of requirement would not automatically update to the latest major version. So the infected version kept spreading. But any developer who decided to audit the package might just look at the latest code on GitHub, version 4, and see nothing wrong. The crime was happening in plain sight, but the evidence was hidden from anyone who looked. While this sounds like a pretty simple strategy, it was in fact incredibly successful. This attack wasn't discovered for months, and only then by complete accident when a developer was examining a build warning. Which brings us to our second takeaway. We can see how the malicious new owner of the EventStream package used this discrepancy between the source code shown on GitHub and the version that got chosen by NPM during the build as a trivial layer for hiding a malicious payload. Essentially, the attackers were relying on tricks involving the way the packages in the NPM ecosystem are distributed. So boltdb and EventStream were two cases where open source software packages were used to inject malware into other software that depended on them. But now let's look at a case where the compromise occurred in the dependencies of the CI/CD pipeline being used to build, test, and deploy software. tj-action/changed files is a GitHub action that allows users to track which files have changed across branches and commits. At the time of the compromise, around 23,000 GitHub repos were using this action as part of their CI/CD workflows. The first steps in this attack took place several months before the attack on the actual TJ actions/change file actions itself took place. In December 2024, attackers abused a workflow in a separate repository to leak a GitHub personal access token of one of that repository's maintainers. They then took no action for 3 months. Seems like they were waiting patiently for the right target to become available, because when the cryptocurrency exchange Coinbase added a workflow dependent on TJ actions/change files, the attacker quickly sprung into action. The attackers used the personal access token they'd compromised from the Spotbugs maintainer as a springboard to compromise more personal access tokens, until eventually they ended up in possession of a personal access token that had write permissions to TJ actions. They then used those permissions to create a malicious fork of TJ actions and override a git tag in the main repository to point it to the malicious commit. This version of the malicious fork injected a payload that dumped the CI/CD runner's memory, exposing sensitive environment variables and secrets directly to workflow logs. Initially, this payload was set to only run when the action was being executed by a Coinbase-owned repository. And indeed, Coinbase did eventually execute the malicious version, which leaked a token with write permissions. However, within less than 2 hours after that, Coinbase had been alerted by a third-party researcher that its CI was using malicious code and the vulnerable workflow was removed. Up to this point, the attacker was very careful to remain hidden. All of their strategies so far had prioritized leaving as little trace and review noise as possible. But after failing to compromise Coinbase, they threw caution to the wind. They opened up the attack to all dependents of TJ actions, with the clear intent of being as visible and damaging as possible. Similar to boltdb, this case involved attackers exploiting the mutability of Git tags, and additionally the way in which GitHub handles forks. A developer might check a Git tag to determine which version of the code to use, and at this point, the tag was pointing to a legitimate and verified commit char. But sometime later, when the CI/CD pipeline actually ran, it ended up fetching a different version of the code. This is capitalizing on the temporal gap between when a human, or even a system, verifies the tag, and when the code linked to that tag is actually retrieved and executed. So in this attack, the use of that Git tag mutability wasn't just to obfuscate. It was to point pre-existing dependencies on a particular tag to malicious payloads. Attacks like these are particularly concerning because they're so recent. Both TJ actions and boltdb were only uncovered this year. This shows that this Git tag manipulation is an evolving strategy, and we can probably expect to see a lot more of it. We'll talk about a number of ways to prevent attacks like these, but I did want to quickly highlight that GitHub has actually recently added a feature to pin dependencies in GitHub Actions to a specific commit, rather than using a mutable tag. So this is really cool. It would definitely be a vital tool for preventing this type of attack, and it should probably be required by default in your projects. Okay, on to our final case study, XC. XC is a data compression utility that's fundamental to nearly every Linux distribution. Last year, the XC compression library was compromised by a state-sponsored actor that had been working for years to take over maintainership and establish trust, even using sock puppets to pressure the existing maintainer into giving them more responsibility. This patient, deliberate multi-year infiltration started in the beginning of 2021, when a new contributor, using the name Geotan, appeared on the XC project mailing list. For almost 2 years, the Geotan user built trust by making innocuous commits to the XC repository, while at the same time using sock puppetry to pressure the existing maintainer into giving away more and more responsibility. All this hard work paid off when around October of 2022, Geotan was officially added to the project as a maintainer. It was only in February and March of 2024 that the malicious versions of XC were actually published, though. These releases contained backdoor binary code that was well hidden inside some binary test input files. When the right conditions were met, a script that was present only in the release, not in the source code on the GitHub repository, would unpack the malicious test inputs to create a backdoor that allowed an attacker unauthenticated, targeted remote code execution. In this case, we got really lucky because it was only a short while later that a software engineer at Microsoft discovered and reported the backdoor, well before it could be widely distributed. But this attack shows us that attackers can use complex build rules and obfuscated payloads to deploy attacks. While the tests were present in the source code, the test input, was present in the source code repository, it was in a binary form. And the script that unpacked it to create the backdoor was only included in the release itself. This provides us with an excellent example of how attackers can leverage that gap between source code or what a human reviews and the built artifact. Which leads us to our final takeaway from these case studies. The source of truth for security is the build artifact, not the source code, because the code that you build is not guaranteed to be the same code that you reviewed. While performing code review is obviously still very important, we don't want to just let anyone check anything into our source code repos. We also need to be really thoroughly examining the build artifacts. But how can we do that? So far, I've been painting a pretty dire picture of the state of open source security. Attackers are leveraging that gap between what humans perceive in code review and what the compiler actually produces or how the package is distributed. What can we do to address this, especially when attackers are continuously evolving their strategies to make it harder for even well-intended reviewers to identify their actions? In all of the attacks we've shown, the attackers targeted a package or workflow via its dependencies. So rather than trying to inject malicious code directly into the target, the attacker compromised the open source software the target was depending on, often using these techniques like typo squatting and git tag mutability to trick human reviewers and hide their tracks. This is a common trend. We find that 98% of the time when a package is affected by a vulnerability, it's affected indirectly via its dependencies. That means that the key to thwarting these attacks is to perform analysis on the build artifacts. So what we get after we've built our source code, which includes resolving and pulling in all the open source packages that we depend on. This means we won't just be analyzing what appears to be the input to our builds, but the actual output of the builds. Which brings us to the capability analysis tool Capslock. Before we talk about the tool itself, let's talk about the model that Capslock uses, which we call capability analysis. We can think of capabilities in the familiar way we might think of mobile phone app permissions. Once upon a time, installing an app was fraught with unknown risks. Will it have camera access or file permissions? Is it secretly doing something dodgy that I have no idea about? At the end of the day, we as users had little choice. We could either install the app, potentially granting it an unknown number of permissions, or we could not install the app. But then the model of app permissions was introduced. Essentially, this is a model for consent. Each app has to specifically request all the permissions it needs. I can see that an app is asking to see my contacts, but not asking for my fine-grained location data. And then I can make a decision about whether I want to install that app based on that. Even better, I have the ability to control what the app can do in some cases. For example, I can grant the app access to my device's location, but only when the app's actually in use. And we can apply a similar model to open source software dependencies. The idea here is that each package already has an implicit set of expected capabilities baked into its functionality. We need to make those capabilities explicit so that developers can build policies around what capabilities they're happy for their dependencies to have, and also to be clearly notified when the capabilities of the software that they're using change. There are several types of capabilities a piece of software might have, some of which should be considered secure or privileged. Things like network access, file system access, or arbitrary external code execution. Obviously, capabilities are sometimes necessary. There are many legitimate reasons for a piece of software to access the network or file system. But these capabilities should only be happening when we expect and understand them. If I'm depending on a maths library to get a square root function, I don't want it to be also reading my file system. Thinking in terms of these capabilities increases the visibility and transparency of how my software and its dependencies behave, which makes it easier to detect possible issues and to pick well-scoped dependencies that don't use more privileges than expected. This is where the Capslock tool comes in. Capslock lets you identify the capabilities in your package and the packages that you're importing. Capslock is an open source tool, which is available on GitHub for you to download, and you can use it as is, or you can modify it for your own purposes. At a high level, you can run Capslock in the path of the package you want to analyze, or just point it at the appropriate path. Once the run is complete, you'll get a report that includes each of the capabilities that got used and how often they get used. What's really cool is that Capslock digs into the software dependencies your package is using, including those transitive dependencies that, as we saw in our case studies, are often the ones causing security issues. It does so by using call graph analysis to work out which functions your software is actually calling. Now, if we were to look only at which packages are being imported, we'd obviously see a lot of false positives. But by looking at the function call level, we can see specifically which capabilities in your dependencies will plausibly affect you. This call graph analysis identifies all paths to standard libraries, even through external packages. And to achieve this, Capslock analyzes the AST that gets built by the Go toolchain, so you can see exactly what you're shipping. And if you're familiar with Go vulncheck, it works in a pretty similar way, but there's some custom modifications due to the different nuances between capabilities and known vulnerabilities. Here's an example of what the full output of the Capslock analysis tool looks like. We can see that this package includes many capabilities, and the ones that are considered particularly unsafe are highlighted in red. When you run the tool, you'll also get a list of all the dependencies that were included in the analysis. If you want more detail, you can use the verbose output that includes call paths to specific capabilities. For example, here we might want to know why this package has a transitive use of system calls, and we can see from the call path that it comes from a terminal coloring library, which is checking to see if it's being invoked from inside a terminal environment. So this tool on its own is already pretty great, but where it really shines is as a supplement to human code reviews. We saw in our case studies that the gap between what humans perceive in the source code review and what the compiler actually produces, or how the package is being distributed by an ecosystem, is getting exploited by malicious actors. But using Capslock to analyze the build artifacts and surfacing that information to humans during code review makes the behavior of the new or changed code more transparent, makes attacks of that kind more difficult. When you depend on a package, you have an expectation that it has a certain behavior. If a package you use suddenly gains a new capability, say when you update it to a new version, you guess that this probably indicates something pretty substantial has changed. That intuition is borne out by the data. When we ran the Capslock tool over every Go package, we found that only 3% of Go package updates add a new capability. Because it is fairly uncommon, when it does happen, it's an event that should trigger scrutiny from reviewers. And we also know that because it's so uncommon, it won't be so noisy that it's adding a bunch of additional toil to reviewers. To this end, we've created the Capslock Git diff tool, a tool that reports on changes in capabilities between two specified commits of a Git repository. These commits can be specified in any way the Git tool understands, such as branch names, tags, or hashes. For example, here we're using the tool to compare two revisions in the foo Git repository. And from the output, we can see that the new capability files, has been added between revisions 1 and 2. In this case, we're flagging that this is a totally new capability, but this tool will also identify new calls to existing capabilities. So even if capability files already existed in this repo, but from a different call, the tool would still bring up that there's been a new call to it. I'm sure you're starting to see how this could be really useful in the real world. Let's go back to boltdb. What did the Capslock results for that look like at the time of detection? Well, this is a real boltdb package, and based on its capabilities, it looks like it isn't doing anything super unexpected. But when we look at the malicious typo squat, the story looks a bit different. On the left, we have the version cached on the Go module mirror, and on the right is a clean version similar to the one that would have been visible on GitHub. When we compare the capabilities between the version in the module mirror and the version visible on GitHub, we can see that it's added some pretty interesting new capabilities, which are highlighted in red. It's fairly typical for malicious payloads like the one involved in the boltdb attack to execute a script and then exfiltrate information across the network. So these capabilities, execution and network access, are exactly what we would expect to see in a malicious change like this. A bunch of obfuscation techniques were used to try and ensure that the injection of this malicious dependency went undetected in code review. We mentioned the use of typo squatting and that huge PR with lots of unrelated changes. But you can imagine that if the maintainers of the cryptocurrency library that was being targeted were running this Capslock diff tool automatically as part of pre-submits, the suspicious changes would have been flagged immediately by looking at the results of the capability analysis. So now we have the tools to analyze not just our source code itself, but the actual build artifacts and what they're capable of. And tools like this are so powerful precisely because they can't be tricked by methods like typo squatting or huge PRs. Additionally, unlike vulnerability scanners that react to known issues, Capslock helps identify potential for harm by revealing unexpected changes to capabilities, even if no specific vulnerability is known yet. This shifts the security paradigm from reactive to proactive. To see the results of some of the Capslock analysis, the Ghost team has run the analysis over the majority of Go packages and made the results available on the deps.dev website. But note that this is only the packages that we were able to build with the default build flags, since we need to actually build the artifacts to analyze them. We've also started analyzing every package we can find on the Go module mirror that has modified Git tags, like what happened in boltdb. These are preliminary results, and we're still looking into them to identify suspicious behavior. We have found some interesting things. Overall, we found that the majority had no capability diffs between that version in the module mirror and the version on GitHub. Of the 8.5% that did have a capability change, most related to changing dependencies, removing tests or demos that were mistakenly published, or trying to fix mistakes such as accidentally leaking private information. As I said, this is just a preliminary analysis, and while we haven't yet identified any new malicious changes, it's possible that there were some, especially among the packages that we couldn't analyze. So in conclusion, support human source code review with code analysis tools like Capslock, which let you analyze your build artifacts to detect unexpected changes in both your software and the transitive software that you depend on. This is a critical step in bridging the gap between what humans perceive in source code review and what the compiler actually produces, or what dependencies you end up using based on how the ecosystem distributes them. Doing so will help prevent that gap being exploited by malicious actors. Another simple thing you can do to protect yourself from those tag mutability attacks that kept coming up is to make sure that you pin your software dependencies by commit, not by tag. Now that you're all convinced that capability analysis is an integral way forward for software security, what's next? Well, Capslock was originally implemented just for Go, but we'd love to see it implemented across as many language ecosystems as possible. Really excitingly, thanks to the Rust Foundation and Alpha Omega, Capslock for Rust is now in pilot, which is so cool, so thank you so much to everyone who helped to make that happen. You can try it now, and I've included a link in the slides. If you've got ideas about automatic capability restrictions, sandboxing, or any other cool things, please feel free to get in touch, scope out a PR, open an issue. We would love to support you. This is how you can contact us, and thank you so much for listening. I think there's a few minutes for questions if anyone's got any quick questions. Yeah?
Thank you, very great talk.
Thank you.
A question, you track except, for example, in Go? So, my answer was like, do you track arguments that the function? Like if arguments will change.
Oh, I see. So the question was, can we track when the arguments to the function changes? I don't believe so. Not with this type of capability analysis, but I mean, that could be a very cool thing to do. But yeah, I don't think in this case that we would be able to have detected that.
But then I can change it from be one time only. I can change malicious arguments.
Yeah. That's a good point. No, I don't think that would be covered by this tool. Hey, yeah.
Any plans for C# ecosystem?
So the question was, any plans for the C# ecosystem? We don't have any specific plans for the C# ecosystem, but if anyone would like to be involved in helping implement it or anything like that, please get in contact. We'd love to support you. It would be great to have this for as many language ecosystems as possible. Okay, cool. Well, thank you all so much.